Well, the question I'm going to answer is this. How would you explain to people in Galileo's time that the light was on an electromagnetic spectrum and there was even invisible forms of this light? So I'm going to show what I would show somebody, but I also want to preface by saying this, and that is that I often have discussions with people where I'm trying to explain to them how these different scientific principles work, specifically with the conservation of energy, some like the second law of thermodynamics, and I've had an extensive knowledge of acoustic energy and specifically photonic systems, meaning photonic and phononic, which means that energy is bouncing between being electromagnetic energy, which is light, and acoustic energy, which is vibration. So also, you can also turn both of those forms of energy into electricity, but that's not what I'm talking about. What I'm trying to say is this, that science is like pretty difficult to explain even in the contemporary era. So I'm going to try my best to actually provide a comprehensive guide to the electromagnetic spectrum. Let's preface this video with a couple things. So we're going to imagine that we're standing in about the year like 1600, because Galileo was born in 1564, so that's where we're going to start off. So we know that the earth is a circle, and for those of you who are like, what is this? It's a whiteboard. It's kind of like your slate tablets. It uses some of the technologies that I talk about today. Don't get freaked out. We also have this thing called a chalkboard, which is in between your tech and my tech, but technology is a lot. So let's start here. Okay. This is the earth. It's a circle, it's a sphere. And why do I say that? I say that because there's this guy named Magellan, and he circumnavigates the entire world. He goes across the entire world. His fleet makes it back. And now, I'm sure you've heard of that story, and I'm sure you've heard of Christopher Columbus. He's the guy who went from Spain to the West Indies. He goes from Spain to the West Indies. So we know that we live in a world that's a circle. Yeah, we knew that. Aristotle knew that. But it's a sphere. It's a 3D circle. So let's just start off with that. So that's pretty crazy that that's going on. Let's look at a biome on this sphere. We have the Earth in all her natural beauty. She has mountains and plants and water and a sky, and these natural orders of the world can be witnessed by the human, who can watch, who can look, who can use his eyes to look at the world that he lives in, right? And by this time, we have an anatomy of the human eye. By 1543, Vesalius of Switzerland does create an anatomy of the eye. So we know that even the anatomical structures of our own human body can be broken down into different parts, the same way that a invention can be broken down into different parts, the same way a chariot is made of multiple wheels. And when we start to think that things can be made of multiple parts, well, we invite the magnifying lens, which is a tool which allows us to zoom in, right? We're standing here to zoom in to the world that we can't see with our eyes. Now, the reason we can't see them with our eyes is because our eyes have geometrical limits. So that's important. Our eyes have limits. They are not capable of seeing everything. They can see some things. So we use these magnifying lenses, and then we start to see things that we couldn't see before. We start to see cellular structures. Now imagine we take a piece of a leaf and we put it under one of these magnifying lenses. Just imagine that the leaf starts to have these interesting cells on it. And maybe instead of a leaf, let's look at a rock or a crystal. Let's look at quartz. When we zoom in deep into this rock or to this crystal, we see this crystal lattice that looks like a big wall of obtuse shapes that pack together into a unique structure. And when we zoom into this unique structure, we get the unit cell. Now the unit cell is how these unique structures are actually what they're made up of. They're the bricks of these crystal structures. So look at this. So we have a unit cell. Now this is one of the more basic unit cells. Not every unit cell looks like this, but imagine that every chemical structure in our universe is made up of a unit cell like this. And these unit cells add together, and when they add together, they create crystal lattices, and those crystal lattices create shapes, and they create tangible materials in the universe. And those tangible materials could be like rocks or crystals, or they could be a little bit more organic, like a living being, or a actual a multicellular life, like a tree or an animal. So these unit cells, each of these little circles, can be understood as having a nucleus and electrons. So what are nucleus and electrons? They are the building blocks of these unit cells. So we are going deep, and we're having to imagine things that we can't see. But we can see them using the right equipment. And if I had the funding to build a microscope or to bring one here with you, I would show you. Maybe I do. You know what? I do have a microscope, so I'm going to show them this stuff with the microscope. Okay. So then we have the atom. Now the atom, like I said, has a nucleus and it has electrons. So let's talk about the electron. The electron is quanta of energy. It's a way of measuring energy. It's a way for us to understand a packet of energy. Now this energy is what the material universe is made out of. And we'll get into that. But I just need you to know that this electron is energy. So everything in our universe is made out of energy. Everything in our universe is made out of energy. All of this made out of energy. That eye made out of energy. This whiteboard made out of energy. This paper made out of energy. I'm not sure that they would have that paper, but if they did. Now, this energy has a geometric and energetic property. This is an atom. Now, this is an atom known as hydrogen. Hydrogen is a chemical, and there's lots of different chemicals. Gold is a chemical. Silver is a chemical. Iron is a chemical. And each of these different chemicals have different corresponding atoms. And based on the chemical, it determines the electrons in the atom. And it also determines the protons in the nucleus, but the protons aren't necessarily important to know about right now. But we need to know that everything in our universe can be understood through these atomical structures. And these electrons have a charge. And this charge creates a field. So, for example, have you ever been a little child and been missing your mama? Well, think of that as like a field. Like that want, that need to go to your mom is kind of like a field, right? Your mom almost produces this energy which makes you want to go and be with her, right? And a field acts on a charge. So when you have this field that's created, it can actually act on other charges. And when a field occurs, it exerts a force on a charge. So it can actually start to pull the charge from where it's standing. So let's look at this. Let's introduce time-space. So you have this charge, which can move from time equals 1 second to time equals 2 seconds, and moves from position A to position B. So these electrons can move. So the electrons that are in every atomic shell, and we talked about atoms are in trees, they're in rocks, they're in our human eye, they're in our human hair. They can move. The energy within them can move. And when you have structures that have lots of different electrons, there's probably lots of movement because all of those different electrons are creating their own field, and they're simultaneously, while creating their own field, having fields created on them. So there's a lot of these arrows going on, and they're going on in all different directions. But we can look at some systems that don't have a bunch of arrows going on. And we can look at the movement of this electron, and we can call it a thing known as current. current produces an electromagnetic radiation. So here's another example of the charge moving. So the charge moves through space, right, in a linear fashion. And when this happens, it creates an electromagnetic radiation. So that means as the charge is moving, that there's actual radiation flying off of it in all directions radially, right? So there is radiation flying off of this charge. And when that occurs, this is light. It is sight. The reason the sun is so bright is because we already discussed that there is a correspondence between electrons and energy, right? And we talked about the fact that the movement of an electron creates light. So it would make sense that our sun has so much light because there's so much energy in our sun. Because our sun is so big, right? It's an energy factory. There's energy flying out of our sun. And that ability for us to see that energy, that is what electromagnetic radiation is. Electromagnetic radiation is light. It is sight. It is what we see. We are able to see things because these electrons are moving and producing light. And it corresponds to how bright something is. So there's a lot of light. There's a lot of energy. The sun, a flying ball of fire. Do we have any questions so far? Yes, sir. Yes, sir. Here. Hey, what's your question? I have 3 questions. First of all, what is a force? What is radiation? And if radiation is everywhere in every single atom, and atoms are everywhere, then how can I see shapes and how can I understand color? Shouldn't there just be everything everywhere? How do I even, that doesn't even make any sense. No, you know what, student? Those are great questions. I actually wrote them down on the board already, so I'm going to answer them for you right now. You asked me some great questions, and I'm going to try my best to explain them. So what is a force? Well, we're not going to learn about what forces really are for another couple decades. There's this guy, his name's Newton. You'll hear about him eventually if you're alive. But what is a force? For this context, a force, imagine this. You're railing in a cattle, livestock, and you get the lasso, you get him, and he pulls on you hard. So you could pull, so imagine this arrow symbolizes how hard he pulls away. And if you pull a little bit, you're not going to pull the cow over there, right? But if your arrow's bigger than the cow's arrow, then you will pull the cow because your arrow's bigger. So that's what a force is. A force is just an arrow that is pulling something in a direction, right? So what is radiation? Well, there's this guy named Planck, but he won't come around for another couple hundred years. But I'll try to summarize one of his laws, which is that temperature is proportional to the wavelength of radiation. So imagine we have a thermometer. A thermometer is a measurement tool which measures temperature, which means if the thermometer is down here, it means it's cold. If it's up here, it means it's hot. So we know that high temperatures are equal to high frequencies. Imagine you have a cauldron of water and you put it over a fire. That cauldron of water is going to start to boil and start to turn into a gas, into a steam. You know that. You've seen that happen before. So the same thing happens with the electrons we were talking about earlier when they're a black body. So this is going to be our black body radiation. This is going to be our black body. So this is the radiation. This is the electric field that it creates. And there's a thing called a magnetic field that it creates too, which also propagates it forward. Magnetic fields are used to guide compasses. The Earth has a magnetic field. They're a subject for another lecture, but they create, based on the temperature, it determines the wavelength. So if you have a low temperature, you have a high wavelength. It means your temperature is long. So like think about an ice cube. An ice cube has like that crystal structure, right? So imagine that the energy in the ice cube when it's cold is moving in these long wavelengths. But as we start to heat up the black body, the same way we heat up the cauldron, we can get higher frequency profiles. right? So in this case, this frequency is higher, but the frequency is lower, but the wavelength is longer. So we can basically have any sort of energy profile based on the temperature that is actually occurring on this, because temperature has a very close relationship to energy, right? So we have this radiation going on. This radiation can be distinct wavelengths, and we can see that this is what it looks like when it's different wavelengths. So if there's different wavelengths of everything, because everything's all different temperatures and all sorts of different stuff is going on, then how does radiation even work, right? If radiation's everywhere, how can we see my hand? Well, shouldn't it just look like a bunch of craziness? Well, we were discussing the geometric limits of the eye, but one of the things that's really cool is that, let's say you have two electrons, they can actually act in entanglement with each other. They can get into a superposition, which means even though you have a bunch of stuff going on, all that stuff going on has a relationship with all the other stuff going on, and they can create a single object and that your eye can perceive. So we call this superposition or entanglement of photons, which means that the electromagnetic radiation produces radiation, which is a photon, which is light, which is energy. That light energy, let's say you have two quantas of light energy. Those two quantas know about each other, and they're able to correspond in what they want to project. And what they project is what your eye perceives, and your eye perceives a single object. That's how it works. It's a superposition. All of these different things going on can all have a big brain together, and they can all produce a single object, a single shape, a single color. We've established that light can be at different wavelengths. We should start talking about how the human actually perceives these different wavelengths. So we have an entire spectrum. It starts with radio waves, then microwaves, then infrared, then visible light, then ultraviolet light, X-rays, and gamma rays. Now, these waves correspond to a wavelength. So radio waves are kilometers away. So they're the waves of seeing distant mountains far from you. You can see what they look like, but you maybe can't see the trees on them. You can see the outlines. As we continue to move in, you can start to see centimeters. Then here is our visible spectrum. And our visible spectrum is comprised of all the different colors that we can see. So you can see we start with the deep purple, and we can be red by the end of it. Now, as we continue to go to higher frequencies of light, we can bring back those cellular proteins that we talked about earlier. We can talk about those unit cells. And as we go deeper, we can see our atom with the X-rays. And as we go even deeper, we can see nanometers. And eventually, right here, you have our picometers, and you have neutrons and protons, which create the nucleus of an atom. So everything we talked about earlier, we've just completely zoomed back. We've zoomed back in, and we see that when we zoom in, it has to do with these. And the way that we can see higher frequencies is by using magnifying glasses, using lenses that zoom in. So these, while being in the space domain, are also in the time domain, as we mentioned. So this is frequency, which is hertz, which is cycles per second, which is a way of measuring what the wave looks like. So that's one cycle. So you see how many cycles you get through in a single second. So we use that to measure. So our eye perceives all these different waves, right? All the different waves hit our eye. And when they hit our eye sends them to a sensor on the back of the eye. And this sensor on the back of the eye has a conversation with the brain. And those conversations lead to chemical reactions in the brain. For instance, when the sky is blue, it releases chemicals which tell our brains to be awake, right? But if we stare at the sun too long, then it'll hurt our eyes. That makes sense because there's such a high level of radiation for sunlight. Now, this also is what allows us to see different shapes, animals, understand different geometries and plants. And the reason that we can only see what's right here is because the human body is a temple, and it's a very smart temple. And it knows that if we could interpret all of these things, that it would probably fry our brain, because these are corresponding with high energy. So if you had all that high super energy in your brain, that obviously, that energy we talked about, it corresponds with higher temperatures. And those higher temperatures can't be withstood by the biological fabric of humans. So that's why when you do have really high wavelengths that you see, they might even burn onto your eye. If somebody stares at the sun for too long, it will burn a spot on their eye. And every time they blink, they'll see that spot. So that is what the electromagnetic spectrum is. And the way you can learn more about it is by using tools which can zoom in from a big world, and they can zoom in to a world where we can see increasingly greater details. And those increasingly greater details correspond to lower wavelengths and higher frequencies. So that's how it kind of works. And I appreciate this. Has taken me a while, and I appreciate you paying attention. Thank you so much for coming to my lecture. Your boy Galileo, he's a great guy, a very smart guy. There's gonna be lots of really smart guys in the future, and a lot of them are gonna be really reliant on what he produced. So stay locked in, y'all, and you know what I mean? Make sure that you can create experimental validation for what you're talking about. And at the end of the day, even if you have experimental validation, people still might not believe you. I know all about that, and it can be really frustrating. So all you can do is continue to work hard, continue to document your discoveries, and work your best to communicate them in intuitive and in ways that are more natural to the human condition. So I appreciate your time today. Thanks for taking a look at the electromagnetic spectrum with me. And that all to say that there's invisible things going on all around us that we can't perceive, and maybe that's okay.